Hello, my name is Katherine Smith, and welcome to my Advanced Functions instructional video. Today I will be answering question 15, part A and B on page 309 of the Nelson Advanced Functions textbook. The question states, describe what happens to the slope of a tangent line on the graph of a rational function as the x-coordinate of the point of tangency, A, gets closer and closer to the vertical asymptote, or B, grows larger in both the positive and negative direction. The question states that it must be a tangent line on a rational function. This signifies that this question is closely related with Unit 3, rational functions and their properties. I will now reread the question and highlight some key elements of the problem. Describe what happens to the slope of a tangent line on the graph of a rational function as the x-coordinate of the point of tangency gets closer and closer to the vertical asymptote, grows larger in both the positive and negative direction. I have highlighted slope of a tangent line as we will first have to determine what a tangent line is and how to find the slope. Next, I've highlighted rational function because we will need to look at the properties of a rational function so we can graph it. Finally, I highlighted closer to the vertical asymptote and larger in both the negative and positive direction because these will be the changes applied to the x-coordinates of the point of tangency to see what happens to the slope of a tangent line on different areas of a rational function. First, I'm going to talk about what the slope of a tangent line is. A tangent line is a line that touches a graph at only one point on a function. Within a small interval of relation, the tangent line could but doesn't have to cross the graph again. The slope of a tangent line is a number that describes the steepness and direction of that line. If the slope has a negative value, it means it only has intervals of decrease, where if it is a positive value, it means it only has intervals of increase. This picture represents a function with a tangent line. The x-coordinate of the point of tangency is underlined in pink. The slope of the tangent line can be calculated using the formula m equals y2 minus y1 over x2 minus x1. M represents the slope. y1 and x1 represent the point of tangency, and y2 and x2 can be found on another point on the tangent line. Next, I'm going to discuss what a rational function is. A rational function can be expressed as f of x equals a of x over b of x. If a of x equals 1 and b of x equals x, then f of x will equal 1 over x, and this will be the function we'll be using today. A rational function can have restrictions in its range and domain. One restriction that this rational function has is that the denominator cannot be equal to 0. This is because 1 over 0 is undefined and can't exist. Since x cannot equal 0, there is a vertical asymptote at x equals 0. The asymptote identifies where the function does not exist. Another restriction that is present in this rational function is that the numerator cannot be equal to 0. This is because in the function f of x equals 1 over x, the numerator is always 1. Since the numerator is always 1, the value of y cannot be 0. This results in a horizontal asymptote at y equals 0. This asymptote also identifies where the function does not exist. Next, we will graph the function f of x equals 1 over x. First, I will draw in the horizontal and vertical asymptotes. Next, I will choose x-coordinates to the left and right of the vertical asymptote. To find the corresponding y values for those x values, I will substitute the x values into the equation. For example, f at 1 equals 1 over 1. This equals 1. Therefore, the y value at x equals 1 is 1. I will follow this procedure to find the rest of the y values. Now that I have found coordinates with both x and y values, I will now graph the function. After graphing, your rational function should look something like this, with a domain of x cannot equal 0 and a range of y cannot equal 0. I have now drawn 6 tangent lines. 3 are on the function in the first quadrant, and 3 on the function in the third quadrant. Each tangent line's x-coordinate of the point of tangency is progressively further away from the vertical asymptote. We will next calculate the slope of each tangent line using the equation m equals y2 minus y1 over x2 minus x1. I have chosen one more point on tangent line B that we will be substituting into the equation as x2 and y2. We will solve for tangent line B's slope together. I have denoted the slope of tangent line B as MB. To find this slope, I first wrote down my 2 points. x1 and y1 are of the point of tangency, and x2 and y2 are another point that I found on the function. To solve for the slope, I did 0 minus 1 and 2 minus 1. That gave me negative 1 over 1. And finally, my final answer was negative 1. Now that we know how to solve for slope, I will now solve for the rest of the slopes using the same method. You may pause the video and also try to solve the slopes yourself. I have written in black the other points I found along the tangent lines. These coordinates represented y2 and x2 when I calculated slope. Now that we know the values of all the slopes, we can answer question A and B of question 15 on page 309. Question A asks, what happens to the slope of a tangent line on a graph of a rational function as the x-coordinate of the point of tangency gets closer to the vertical asymptote? We can see mathematically that as the x-coordinates of the point of tangency get closer to the vertical asymptote in the first and third quadrant, the slope of the tangent line increases in value. For example, the red slope has a much higher value than the blue slope and is also much closer to the vertical asymptote. Same within quadrant 1. We can also see visually that the tangent lines with the x-coordinates closer to the vertical asymptote are much steeper. This results in a larger slope value. If the x-coordinate continues to get closer to the vertical asymptote, the tangent line seems to become almost vertical. I will demonstrate with my ruler. As the x-coordinate of the point of tangency is close to the vertical asymptote, the ruler is very steep, but as it gradually gets further and further away from the vertical asymptote, it becomes much shallower. In conclusion, as the x-coordinate of the point of tangency gets closer to the vertical asymptote, the slope of the tangent line increases and becomes visually much steeper until it is virtually parallel with the vertical axis. The y values approach positive and negative infinity as the x values approach 0. Using the same 6 tangent lines, we will now answer part B. Part B asks, what happens to the slope of a tangent line as the x-coordinate of the point of tangency becomes larger in both the positive and negative direction? Mathematically, in the first quadrant, we can see that as the x-coordinate becomes larger in the positive direction, the slopes decrease in value. Slope C has a much smaller value than slope A. This is also occurring in quadrant 3 as the x-coordinates are becoming larger in the negative direction. We can also see visually that the slopes of the tangent lines becoming more shallow as the x-coordinate becomes larger in the positive and negative direction until it is almost completely horizontal. I will demonstrate this again with my ruler. It's very steep as the x-coordinate is close to the vertical axis. But as the x-coordinate approaches infinity, the tangent line will become almost parallel with the y-axis. In conclusion, as the x-coordinate of the point of tangency becomes larger in the negative and positive direction, the slope of the tangent line decreases in value, resulting in a very shallow line until it is almost parallel with the horizontal axis. The y values will approach 0 as the x values approach positive and negative infinity. A pharmacist could use rational functions and the slope of tangent lines to determine different dosages of medication required for different individuals. Thank you for watching my advanced functions instructional video. I hope it helped!